So in the last video, we left off talking about slope as a rate of change, and we said that for a linear function, which is a line of course, that rate of change is constant. So what we want to look at here is what if we don't have a linear function, but we're still going to think about the rate of change. And we're just, again, going to draw just in the first quadrant, so we got less things in the way in our diagram. So maybe we have something that looks like this, y equals f at x. So in a line, well, maybe I'll draw a line here. I drew one last time, but let's do a different one. Okay, so we have this line. You take 2 points on the line, and you want to find the slope. Let's say we have 3 points here. If you go up, your change in y over your change in x is always the same. It's constant. If you go up the same amount and then over the same amount, you're going to end up back on the line, right? But with a nonlinear function, if you take 2 points and take the change in y over change in x, this one you have to go down and then right? So this, if you think about this rate of change from to get from here to here, it's actually negative. Then when you go from here to here, you go up and over. Now we have a positive rate of change. So if we take, I use a and b, say this is a and this is b, you can take various points in here and get different slopes. The average rate of change will actually be the slope of the line that goes through a and b. So different points give a different slope, of course. This line is called the secant line through the ordered pair a, f at a, and b, f at b. All right, so the average rate of change, if you know the formula for slope, you know the formula for the average rate of change. And I usually will abbreviate average rate of change like this, AROC for average rate of change. We're going to use function notation, however. So if we know that's a function f, a would correspond to the y-coordinate f at a, b to the y-coordinate f at b. So we've got the change in y. Instead of using y2 minus y1 like we do in the slope formula, we're going to do f at b minus f at a. Oops. And then the change in x is b minus a. Now the textbook might use x1, x2, f at x2 minus f at x1 over x2 minus x1. It's the same thing, it's just using different variables for your, the beginning of your interval and the end of your interval. So this is an interval here from a to b. So the average rate of change is the slope of the secant line through those ordered pairs that I just wrote up here. So that we've got lots of different rates of change given any 2 points. In calculus, you'll talk about this idea of the instantaneous rate of change, and that's basically what's going to happen if at a single point, what's the rate of change. And I don't want to get into that, but you talk about letting 2 points get closer and closer together, and what's the slope of the tangent line then. A tangent line would be something like this. That's all to come in another course. But for now, just kind of getting the wheels turning for that sort of discussion when you get to that class. You need to understand what secant lines are and average rate of change before you can do that. Okay, so let's go ahead. We're just going to do just a straightforward problem. Find the average rate of change of the function f at x is 2x squared minus 3 from a equals -1 to b equals 3. All right, so the first thing, you've got your interval from a to b. A is, -1, b is 3. And then you need the function values, so that you need the y-coordinates, basically. So f at -1 just plug it into f to find that. 2 times negative 1 squared minus 3. This 3 is negative 1. So your ordered pair here is negative 1, negative 1. F at 3 is 2 times 3 squared minus 3. So that's 9 times 2, 18 minus 3, which is 15. So, you know, basically you're finding the slope through these 2 points, negative 1, and 3, 15. Okay, so our average rate of change, 15 minus negative 1. Well, here, let me write it in the notation first, and then I'll plug the numbers in. So it's f at 3 minus f at negative 1 over 3 minus negative 1. So of course the output should match up with the corresponding input when you plug this in. You don't want to flip these. So we already found f at 3 is 15 minus f at negative 1 is negative 1. And then we already plugged in 3 minus 1, that's going to be 4. So we get 16 over 4, which is 4. Okay, if we want to interpret this, we would want to look at the graph of 2x squared minus 3. And if you don't remember how to do that, that's okay. We're going to review soon all of our common graphs for our algebraic functions and using transformations. We're going to review that, but I'm just going to go ahead and graph this. And you can use a calculator if you need to. You go 1, 4, 8. Be here and here. What did I do? 2x squared minus 3. Sorry, I'm just thinking because this shouldn't agree here. What did I do? 2. Oh, I'm plugging in like I went two steps away and I only went 1, so it should go up just 2 units. I'm sorry. And then when you go up 2, then it goes up 8 units. Sorry for the long pause. Okay, I don't know what I was thinking. All right, so this is our 1, negative 1. And this is 1, negative 1, and negative 1, negative 1. Excuse me. And this point would be 2, 4. Whoops, no, 2, 5 actually. Goes up 8. I'm not going to redraw it. Let's just make my units a little smaller. I'll cheat. The graph actually looks good. I think my units are too big. 1, so this is going to be 5 here. So this is 2, 5, and negative 2, 5. Okay. Sorry, that shouldn't take that long to graph. All right. I mean, as long as it took me. So we go through negative 1, that's this point, and then we also have the 315. That's going to be, that was 5. Unfortunately, I put this in a bad position here, but it's going to be like way up here, 315. So this keeps going. And then this 4 that we found is actually the slope of this line, m equals 4. Okay? Sorry, that went out through that notation there, but just so you get the general idea. All right, well, let's look at the last problem, which is an application of this. So we have an athlete run, I'll just read it here. An athlete runs the 100-meter dash in such a way that the distance d at t run after t seconds is given by this function here. D at t is 1/5 t squared plus at, and that's a quadratic function. Find the average rate of change of the runner for the race. Okay, so we need to know, to answer this question, average rate of change of the runner for the race, we need to know the his start time and his end time. We know the length of the race was 100 meters, right? So, basically how long did it take him to run that 100 meters? So his start at the beginning, or initial position, of course, would be 0 meters. So when you plug in 0 seconds, you get out 0 meters, right? So this is in seconds. That's time. So our first order pair is 0, 0. So we plug in time, we get out distance. All right, at the end of the race, what we don't know is how long it takes him to run it, but we know it's over when he hits 100 meters. So we need to find this value. Let's, instead of a variable, let's call it T2, and then for this one, this was T1 is 0 seconds. Okay, so at T2, we need to find that. So we have 1/5 T2 squared plus 8 T2 should equal 100. Just plugging T2 into our function here. Okay, so this is a quadratic. I mentioned this is a quadratic already. We're going to move everything to one side, but before we do that, let's get rid of that 5, because I don't want to have any fractions. Even if I have to use a quadratic formula, I don't want to plug fractions in. So I'll take everything times 5 to get rid of that 1/5. So I've got T2 squared plus 40T2 is 500. Now move everything to one side. And then if this does factor, we'll find factors of negative 500 that add up to 40, which we can find. It would be 50 and negative 10. If that didn't factor, then go ahead and use a quadratic formula. So we've got T2 plus 50 times T2 minus 10 equals 0, which implies T2 is negative 50 or T2 is 10. And of course the negative 50 doesn't make sense. We can't go back in time. And so it took him 10 seconds to run the race. Okay, so the problem's set up to have a nice exact 10 seconds, right? But in reality, of course, it could not be as nice. But here we go. So now we know that our second ordered pair, when we plug in 10 seconds, we get out 100 meters. Okay, so the average rate of change for the runner, I'll just use my notation I said I would use, average rate of change. This is the change in the output, which is the change in the distance. So he ran 100 meters, right? He started at 100, or he started at 0, but he ended at 100, and then it took him 10 seconds. And he started at 0 seconds. I won't put the S in there, but I'll talk about the units in a second. So we've got 100 over 10, which is 10. And the units, you know, these were meters and these were seconds, so this is 10 meters per second. So what we have here, because this is meters per second, this is his average speed to run the race. Now, of course, he didn't run 10 meters per second for the entire race, right? And that's why we call this an average. It's a, you know, sometimes he was going slower, of course, at the beginning. It takes him a while to get up to that speed, and then at some point in the race, he has to run faster than that in order for it to average out and get 10. If you think about the graph here, I'll just do a quick sketch. So when you plugged in 0 seconds, right, this is seconds and this is meters, he hasn't started yet, so you've got a position of 0. And then after, let's just put 10 seconds here. Now this isn't going to be to scale, but you know, let's say this is 100 meters here. And this is a quadratic, so it has a curve to it. It's not a straight line, but it's fairly flat just because of the, you know, 100, the scale. If you had this to scale, it would almost look linear, is what I'm trying to say. But there is a curve here. And so this 10 meters per second is actually the slope of this secant line. but his true speed at any given point, of course, is changing. And if you take calculus, you'll find out that that speed at any given point in time is actually the slope of what we call the tangent line at that point. So notice this slope down here is not as large as it is like right here. So what that tells me is he's running faster right here than he is right here. Again, that's getting ahead of things. What I want you to understand right now is just this average rate of change. But that kind of gives you a little tidbit of what would come us.